Okay. All right. Today, new learning target. Learning target 7.2. Officially, I have it written up over here. Don't worry about moving the camera. I'll just talk for loud. 7.2 is write and solve exponential equations. Write and solve exponential equations. And I kind of added this simplify exponential expressions to that as well, because we will spend a little bit of time simplifying exponential expressions. That's kind of review though, really. You know, it's really just exponent rules. So, new learning target: solving and writing exponential equations. You guys graphed them before, okay? You graphed them before. Now we're going to write and solve some exponential equations before we get to the story problems part of it, or some application problems, if you will. Okay? Little refresher. All the graphs you are to have done usually took this form, for the most part. Okay? Y equals A times B raised to the x power, where A represented what? Anybody remember? Look in your notes. The y-intercept. Yep, A was usually the y-intercept of our starting amount. And B was the number you're multiplying by over and over and over and over again. Okay, and then notice where our variable is now, because we're working with exponential functions. Our variable is up in the exponent. Okay? Alright, so then some of the ones that we looked at in class, or maybe you saw in your homework: y equals 3 times 2 to the x, y equals 4 to the x, y equals 5 times 1/2 to the x, y equals 1/3 to the x, okay? Those are some examples of some different exponential functions. Some of the functions were growth, some of them were decay, some of them were actually upside down, like the one we just did here to start class, okay? But if all the numbers are positive, you're either going to have growth or decay. For instance, y equals 3 times 2 to the x. Is that going to be growth or decay, and how do you know? Growth, because if what's smaller than 1, it's going to be decay. Or the b value, the number you're multiplying by over and over and over again. If you start at 3 and you keep multiplying by 2, what's going to happen? Gets bigger, right? Goes up, increases, exponential growth. Okay? This one is just 4 as your b value, definitely bigger than 1. If you keep multiplying something by 4, it's going to get bigger. Okay? How about this one? Decay, because the b value is between 0 and 1. It's smaller than 1. If you start at 5 and keep multiplying by 1/2, 2.5, 1.25. I don't know in decimals, that's why fractions are easier. 5, 5/2, 5/4, 5/8, 5/16, 5/32. Okay? Cutting fractions in half are a lot simpler. Okay? You'll get smaller. 1/3 to the x power. If you multiply something by 1/3 over and over and over again, it gets smaller. Those would be exponential decay. So these, the growth ones, would look like this. The decay ones, you know, look like that. Okay, they level off and approach 0. So that's kind of what we talked about in 7.1, is just what the graphs of some of those exponential functions would look like, what the a and the b values represent, and so on. Okay, so again, just a little refresher. Now, oh yeah. Might help.
Nice one.
Yeah. Okay. Now, all of these, okay, all of these, if you notice, kind of have numbers you're used to seeing: 3, 4, 5, 1/2, 1/3, different things like that. Okay? A lot of times with exponential functions, you will see an e.
You're like not in it.
What's that?
You're like not in it.
That's okay.
Okay.
You just need to hear what I gotta say. That's probably perfect then. All right? E is something that you will start to see in exponential functions. Okay? E is a number. E is like pi. Right? Back when math was being invented / discovered, whatever you want to call it, okay? If you think of pi, all right, pi was kind of discovered in a sense, because what they found out was if you figure out how far it is around a circle, and you divide that by how far it is across the circle, no matter how big or small the circle is, this same number kept showing up, 3.14 something, something, something. That's pi, okay? So the ancient Greeks labeled it pi. We know it, pi is 3.14, goes on forever, it's an irrational number, that sort of thing. Okay, but it shows up a lot in geometry. Pi, you use it, a lot of circular things. Okay, you're going to use pi a lot. In nature, in percent increase, exponential growth and decay at times. There's another number that started showing up a lot. Okay, it was this number is about 2.718, so on. We'll use it in class here. Okay, but the guy that discovered it, his name was Euler, E-U-L-E-R. His last name started with an E, so he labeled it E, I guess. I don't know. Okay, there's some really fun math history there for you. Okay, math history was a terror. What's that? Yeah. Try taking a math history class by a guy that looks like he was old enough to have seen all of math history. I mean, it was terrible. Okay? I can probably say, I'm guessing he's dead now. All right? That was a really fun class. I know it's on video, I don't care. Probably doesn't even know YouTube is. All right? All right. Anyway, E is this number that ends up showing up a lot in exponential equations, and so E is another number, all right, that we will use a lot, especially in this chapter when it comes to exponential growth and decay. Here's what you need to know. E is about 2.7 something, okay? E is about 2.7. You don't need to memorize a whole bunch of decimal places, okay? On your calculator, if you look at your calculator, towards the bottom left side, you'll see an LN button. And right above that LN, you'll see e to the x power. Okay, seeing it?
Yep.
Bottom left, LN. Look for a key that has a big capital L, capital N on it. Okay? Bottom left-ish. All right? Right next to the 4, kind of. Okay? Just left of the 4 key. You'll see an LN right above it says e to the x. Or find your division key. Look above your division key. See the little E there? Both of those would work, all right? Both of those represent the number E, okay? So again, know where it is on your calculator. Know that it's a little bit smaller than 3. That's all that you really need to be concerned as far as using it. I'll teach you how you'll use your calculators here shortly, okay? But, so anyway, so we got E. E works just like anything else. Okay? E is a number. Keep that in mind. Don't be fooled if you see an E. We're not trying to trick you with anything. If I ask you to simplify this expression, simplify e to the 5th times e to the 4th, it works just like any number would. What's your answer? E to the 9th, because when you multiply, you add exponents. So e to the 9th. E to the negative 3 power works like anything else. You can't do negative exponents. So what do you do when you have negative exponents? Make it a fraction. Move it downstairs. All right? E to the negative 3 would be 1 over e to the 3rd. That's it. Good enough. Two e to the 4th times itself 3 times, or all of that raised to the 3rd power. You can either multiply by itself 3 times, or just raise both things to the 3rd power. 2 to the 3rd power would be 8. Okay, good. Nobody said 6 in this class. That's good. Usually it's guaranteed 6. Okay. E to the, I know. E to the 4th to the 3rd power. Power to a power. What do? So e to the 12th. Okay.
How do you find E?
Okay? Probably by working backwards from exponential equations using logarithms, which you learn later.
I'm lost.
With
No,
what?
literally, not this. With conversation.
Oh, gotcha. All right. So far, so good? No different than any number, right? Okay. Do a couple more here. Let's say I get a little more complicated. E to the 5th times e to the 2x times e to the negative 1. Everything's just being multiplied together, so we still do what to the exponents? Add them. 5 plus 2x plus negative 1. What do you get?
E to the 2x plus
2x plus 4? They're not like terms, can't combine them, right? Can't write 6x, so you just write e to the 2x plus 4. Or 4 plus 2x, I don't care. Okay. E to the 2x plus 4. Division. When you divide, what do you do with the exponents? Subtract. So if it was e to the 10th divided by e to the 6th, it'd be e to the 4th, right? Well, what's this going to be? E to the what?
E to 2 minus x.
2 minus x. 2 minus x is 2 minus x. They're not like terms, so leave it. E to the 2 minus x power.
Will you ever give it to us like that, and then let's go switch it back? Like
From
right
here
back?
to here.
Yeah.
I'm going to give you fractions or things multiplied together or radicals and just ask you to simplify them. That's it. I'm not to 15 yet, am I? Okay, this is the last one, so just want to make sure it fits. Oh, no, maybe it's not. What am I at?
11.
Okay. The 4th root of 16e to the 8x. So what times itself 4 times equals 16e to the 8x? Some of you might be able to do that mentally.
2.
2 what?
E.
2e to the 2x power. 2e to the 2x power. Because 2 times 2 times 2 times 2 is 16. E to the 2x times e to the 2x times e to the 2x times e to the 2x would be e to the 8x. Final answer, 2e to the 2x. Some of you are thinking, I can't do that in my head. Okay, I'll show you another way. Alright? The 4th root really means you could raise it to what power? 1/4 power, right? The 4th root means 1/4 power. Did that last chapter? So you have 16e to the 8x raised to the 1/4 power. Alright. 16, raise it to the 1/4 power. You don't know it off the top of your head, get out a calculator. 16 to the 1/4 power is going to give you 2. E to the 8x to the 1/4 power. When you got a power to a power, what do you do with the exponents? Multiply. What's 8x times 1/4? 2x. So just because you can't do it in your head doesn't mean you can't use exponent rules to help you figure it out. My point of all this, simplifying with e is just like simplifying with any variable or any other number. Okay? E is just like any other number. Any questions so far? Don't need to write any of this next stuff down. If I asked you to graph y equals e to the x power, is e bigger than 1? So therefore it's going to be exponential growth. Right here, that solid blue graph, that is y equals e to the x power. Okay, that's that one right here. Somebody in the other class said, well, what if you throw a negative sign in front of it? Okay, well, if you throw a negative sign in front of anything, it reflects it over the x-axis. So do you see this dashed one right down here? That's y equals negative e to the x power. It just took that graph and reflected it over the x-axis right down here. Again, not something you have to know. I'm just showing you it works just like any other number. Okay?
Will you give us one like the?
We don't have to graph any of the e's.
Okay.
Yeah, the graphs will be like the 8 that you had to do, or like, you know, a little bit like the one that I gave you here first. Okay. Someone said, well, what if you make the x a negative? Okay, well, can you do negative exponents? No, move them to the bottom. 1 over e to the x. Well, think about it. 1 over e. Is that bigger than 1 or smaller than 1? 1 over e. Smaller than 1. It's almost like 1/3, isn't it? Because e is almost 3. So it's kind of like 1/3 to the x power. So what do you think you're going to see? Exponential decay. Alright? So again, I'm not asking you to graph any of these, but I'm showing you. They're just, e is a number. Okay? That's the point I'm trying to make. If the book has a couple problems that says evaluate e to the 5th power, get out your calculator, type in e raised to the 5th power, press enter, and get your answer.
Are we supposed to stop it?
Okay. Stop. Did I go over?
No.